In this lecture, we are going to talk about returns. People often talk about the return on investment. That's exactly the kind of return we want to discuss. What does return mean? How do we calculate it? Are there different kinds of returns? We will answer these questions in this lecture. Returns can generally be thought of as a percentage. I like to think of them as the same way I think of a sale when you're shopping, but with the signs reversed. So for example, if you see a product that costs $100 normally, but is 20% off, that means you'll pay $80. Similarly, if you invest $100 today and got back only $80 tomorrow, then your return would be minus 20%. Of course, that's not a very good return since we would usually like our investment to increase in value. To be more accurate, we define the net return as follows. Returns are always defined over some time period, whether that's over a day, a month, a year, or even a minute. So, given some time period, assuming no dividends, the net return is calculated as the final price minus the initial price, all divided by the initial price. Using algebra, it's easy to see that this is equivalent to the final price divided by the initial price minus 1. And remember, this is called the net return. But sometimes we simply refer to it as the return. So if I ever talk about the return without qualifying what kind of return I'm talking about, you can assume it's this. Note that another way of writing the return, which I find to be more expressive, is to index the prices by time. So the net return at time t is equal to p at time t divided by p at time t minus 1. This is also equivalent to p at time t minus p at time t minus 1 all over p at time t minus 1. Now, even though this is pretty trivial, let's do a simple example just to make sure everyone is on the same page. So suppose that my initial investment is $100. I get back $120. Therefore, my net return is 120 minus 100 all over 100. That's equal to 20 over 100, which is equal to 20%. It's clear that if we lose money, our net return will be negative. So for example, if my initial investment is $100 and I only get back $80, then my net return is 80 minus 100, all divided by 100, which is equal to minus 20%. Sometimes we like to express the return as a ratio of the new value to the old value. This is called the simple gross return. We don't normally have a symbol for this, but rather, we just write it as 1 plus R of t, where R of t is the net return. This is useful because it tells us relatively how much our investment has increased or decreased compared to the number 1. For example, if my initial investment is $100 and I get back $120, then my gross return is 1.2. That is, I got back 1.2 times what I originally put in. If my initial investment is $100 and I get back $80, then my gross return is 0.8. That is, I got back 0.8 times what I originally put in. And of course, if my investment doesn't change, then my gross return is just 1. It should be easy to see that this is exactly related to the net return, which we just discussed, and all I've done is added 1 to both sides. Finally, we have the log return, also known as the continuously compounded return. The log return is very important, yet very strange. We don't walk into a store and say, "What can I buy for 8.5 log dollars?" We'll see later in this course why log returns and log prices are convenient for modeling the movement of stock prices. Until then, let's try to understand the definition. The log return is just the log of the gross return. In other words, it's log of 1 plus R of t, which is the same as log of P of t divided by P of t minus 1, and that's also the same as log of P of t minus log of P of t at time t minus 1. Note that it's sometimes conventional to use lowercase letters for log returns and log prices. So little r of t is equal to log of 1 plus big R of t, and little p of t is equal to log of big P of t. And so the log return is just the difference in log prices. Intuitively, we can see why log returns and log prices are convenient. Instead of having to do multiplication and division, we can simply do addition and subtraction. So the log is an interesting function, especially in the context of finance. As you'll soon see, returns generally take on very small values, very close to zero. In fact, financial engineers often don't even discuss returns in natural units like percentages, because they're often in the realm of fractions of percentages. In other words, if you used regular numbers, you'd see lots of zeros after the decimal point. For this reason, financial engineers often use units called basis points, where 1 basis point is 1/100th of 1%. In other words, a basis point is 1% of 1%. And so returns taking on such small values has an interesting effect on log returns. Specifically, we know that for small x is approximately equal to log of 1 plus x. If you're not convinced of this, you're encouraged to draw a graph such as this one as an exercise. This means that whether you are looking at log returns or non-log returns, they will all be approximately equal. That means when we look at their distributions, they will also be distributed roughly in the same way. Let's do an example with cumulative returns. Suppose I'm given the daily return over an entire year. That's 252 returns and an initial price, P0. I want to calculate P of 252. That is the price at the end of the year. It's important to remember that returns compound. In fact, we can understand this simply by rearranging the equation for the return we had earlier. So P1 is equal to P0 times 1 plus R1. P2 is equal to P1 times 1 plus R2, but that's also equal to P0 times 1 plus R1 times 1 plus R2. And therefore, P at 252 is equal to P0 times 1 plus R1 times 1 plus R2, all the way up to times 1 plus R252. Suppose we wanted to know the average daily return. That is, what return, if I got the same return daily over the year, would result in the same final value, P of 252. Well, we can calculate that by saying P252 is equal to P0 times 1 plus R to the power 252. This is the same formula from earlier, except we can combine all the 1 plus R's together, since now we want the same R. We can also equate this to our previous expression so that we can find R in terms of the daily returns over the year. After rearranging, we get that R is equal to the product from I equals 1 to 252 of 1 plus Ri, all to the power 1 divided by 252, all minus 1. As you may know, we call 1 plus R the geometric mean of all the 1 plus Ri's. Now let's consider what would happen if we use the log returns instead. If we take the log of both sides of our previous expression, we get that 252 times log of 1 plus R is equal to the sum of all the 1 plus Ri's. Therefore, little r is just the arithmetic mean of all the daily log returns. As a final note for this lecture, I want to say that, depending on where you look, you may see different definitions for different types of returns. Generally speaking, I want to avoid a terminology in this course as much as possible, and pay most of our attention to the mathematics, since that's the most important and unambiguous. So if you've seen other definitions in the past, just put those aside for this course.